Before we dive into Lagrange theorem, let's first understand the basic of group theory. Group theory helps us describe structure and symmetry in many real-life systems, like rotation of object, flipping a shape, or even clock arithmetic. So, what is a group? A group is a set with an operation that follows 4 key rules. Let's say we have G, and the operation is binary, either addition or multiplication. So, for the closure, if A and B is in G, then A star B is in G. Second, associativity. If A star B in bracket star C equal to A star B star C in bracket. And the third one is identity. There's an element E which is identity such that if A star with identity, we will get A. And the last one is inverse. Each element A has an inverse such that A star inverse will equal to identity. So the example is integer modular n with addition. So basically, integer modular n with addition is a group since it follows the 4 properties. So let's look at a familiar example, the hours on a clock. This is a group non-n integer and the modular 12. The set is between 0 until 11, which represent the hours on a 12-hour clock. So, to convert from the 24-hour clock to the 12-hour format, we can use modulo 12. For example, if we have 15 in the 24-hour system, it will become 3 p.m. since 15 mod 12 is equal to 3. Now, what if we take a smaller set from elements from a group and check if it's still a group? This smaller set is called a subgroup. So, what is a subgroup? A subgroup must also satisfy the same group properties as the original group. For example, in the set form of a subgroup under addition modulo 12, 0, 3, 6, 9 is one of the subgroup. So, if the whole group has 12 elements, only value that can divide with 12 is a subgroup. That's what Lagrange theorem explains.
In this part of our video, we will explore Lagrange's theorem, what it really says, and how it relates to subgroups and individual elements inside a group. We will also take a closer look at something called cyclic subgroups, which are created by taking powers of a single element. Lagrange's theorem states that if we're working with a group that has a finite number of elements, then any subgroup we can form will have a size that divides evenly into the size of the whole group. So if the full group has 12 elements, possible subgroup sizes could be 2, 3, 4, or 6. This simple rule actually tells us a lot about how groups are built. Think of a group like a cake. A subgroup is like one slice of that cake. The entire cake can be divided into identical, non-overlapping slices, each the same size as the subgroup. These slices are what we call corsets. They are just shifted versions of the subgroup, and they tile the whole group perfectly. That is what Lagrange's theorem all about, that the group is made of evenly sized pieces. Let's look at what happens when we focus on just one element in a group. If we take that element and keep combining it with itself over and over again, we start to see a pattern. Eventually, the result circles back to the identity, the element that leaves everything unchanged. This process creates a loop, and this loop includes only a few elements from the whole group. This loop is what we call a cyclic subgroup because it is generated by cycling one element repeatedly. So from one starting point, we build a small group that follows the same rules as the big group. The number of unique elements that one element can generate is called its order, and here is something important. The order of the element always divides the total size of the group. So even when we zoom in on a single element, Lagrange's theorem still holds true. It helps us understand not just subgroups, but how individual elements fit into the bigger picture. Let's see how this works with a real example. We will use the group of integers from 0 to 11, with addition done in a circle. This is called mod 12. Now pick the element 3. If you keep adding 3, you get 0, 3, 6, and 9. That is subgroup with 4 elements, and since 4 divides 12, it fits the rule perfectly, so the element 3 generates a cyclic subgroup of size 4. To wrap up this part, Lagrange's theorem says that every subgroup fits evenly into the whole group. Cyclic subgroups created by the individual elements also follows the same rule, so both subgroups and elements are deeply tied to the structure of the group.
Let's understand the relation between groups, subgroups, and cosets improving the Lagrange theorems. Now, we all know that a group is a set with the binary operations that follow group axioms. A subgroup, on the other hand, is a subset of a group G that's also a group. Every group has at least two subgroups, which is itself and the trivial group. The trivial group consists of a single element, which is the identity element. Then, how do these subgroups related to the group? That's where the coset comes in. A coset is what you get when you take every element in the subgroups and shift them using another element from the group. There are two kinds of coset. First one is a left coset, where you combine an element G from the group G to every element in the subgroup H on the left side. A right coset is another coset which is the same as the left coset, but you combine it on the right side. Let's take a look at an example of cosets. Let G is equals to Z modulo 6 under additions, and let H, or the set of 0 and 3, is the subgroups. Then let's compute them for each G in G for the left cosets. First one, 0 plus H, we got a set of 0 and 3, which is the H itself. Second one, we got 1 plus H, which we got set of 1 and 4, another coset. And then 2 plus H, we got a set of 2 and 5, another coset. And then we got 3 plus H, and we got a set of 3 and 0, which is the same as the first one, which is 0 and 3. So there is no new coset. And next, we got the 4 plus H. We got a set of 4, 7, which is congruent with a 4, 1, same as the 1 plus H. And next, finally, we got a 5 plus H. And we got a set of 5 and 8, which is congruent with the 5 and 2, same as the 2 plus H. Finally, we've got 3 of distinct cosets, which is the set of 0 and 3, sets of 1, 4, and a set of 2, 5. Why cosets important? Cosets are important because they partition the entire group, meaning that it separates into equal non-overlapping parts covering G. All cosets of H has the same size of the subgroup of H. Together, all cosets cover every element of group G, meaning that no element are left out or counted twice. Second one, cosets helps to understand the structure of groups. By looking at how groups breaks into the cosets, we see how the subgroups fits inside the bigger groups. This leads to the idea of the index of a subgroups, which is how many cosets there are. And finally, the coset is the key in proving the Lagrange theorem, which stated that if a G is a finite group and H is a subgroup of G, then the order of H divides the order of G. Let's say we manage to split G into non-overlapping cosets. Then the order of G is N and the order of H is D. Let the number of cosets be K. The number of cosets is called the index of H in G. So we have D multiply K equals to N. In other words, D divides N. This means the order of H divides the order of G. Hence, this proves the Lagrange theorem.
Lastly, I will explain about the application of Lagrange theorem How this theorem helps us to understand the structure of groups. The first one is Lagrange theorem helps us to predict or reject possible subgroup sizes. The order of a subgroup must divide the order of the whole group. For an example, if the group has 12 elements like Z12 or another group of order 12, then the only possible subgroup orders are 1, 2, 3, 4, 6 and 12. 5 would not be a subgroup because 5 doesn't divide by 12. Now, let's look at a specific example, the symmetric group S3, which is the group of all permutation of 3 objects. Since there are 3 factorial equals to 6 possible ways to arrange 3 objects, the order of S3 is 6. According to Lagrange theorem, any subgroup must have an order that divides 6, that is 1, 2, 3 or 6. And indeed, we can find this subgroup of each of these sizes. The subgroup with only the identity permutation has an order 1. The subgroups like E12, E13 and E23 each have an order 2. The subgroups like E123, 132 has 3 elements and it forms a cyclic subgroup. And the last one, the whole group of S3 is a subgroup of itself with an order 6. So, every subgroup we find in S3 has an order that divides 6. And this is what exactly Lagrange theorem tells us should happen. Lagrange theorem also tells us something important about the elements of a group, which is the order of any element. Lagrange theorem states that the order of an element is equal to the order of a subgroup it generates. In Zn, the element 2 generates 0, 2, 4, 6, and the element 2 has order 4. This is because 2 plus 2 plus 2 plus 2 is equal to 0 would add. And yes, this is true because 4 can be divided by 8. To conclude everything, Lagrange theorem is a powerful tool for studying groups. It helps us check if a certain subgroup sizes are possible, understand the structure of a group, and know more about the elements inside it. But we need to remember, the Lagrange theorem only tells us what is possible, not necessarily what exists.